Alright, this is a problem dealing with static friction and the block is not moving, so we're going to have to use a force analysis on this. So the first step is going to be to identify all the forces on each block and complete our free body diagram. So block A, we've got normal force, there's gravity, which has a perpendicular component and a parallel component. Perpendicular component is mg cosine 25, that angle is 25. The parallel component is mg sine 25. We're dealing with static friction here. And what's more, if you read the problem carefully, it says what is the maximum mass of block B for which block A would remain at rest. So that means the block is just about to move because mass B is at its maximum value. That means that the force of static friction is at its threshold. It's at its maximum possible value. So we're able to substitute that in. In addition, we've got tension on block A. So those are the four forces acting on block A. I will go ahead and take down the ramp as positive. It's kind of arbitrary. And if I'm going to maintain a consistent sign convention, then the downward direction has to be positive for B. And for mass B, we've got the tension force that points up, which is the same tension force over here that acts on mass A. And we've got gravity, mbg, which points down. Alright, so let's see. And like I said, I can say that the force of static friction in this problem is equal to the maximum possible force of static friction, which is mu sub s times the normal force, since it's a threshold problem. Alright, so I've got my free body diagram completed. There's no motion to indicate in this diagram because we're assuming it's not moving, so I just have to identify my forces and my sign conventions, and now I'm ready to write down force equations. So I'll start for mass A. The sum of all the parallel forces is Ft, that's positive because it points down the ramp, mag sine 25. That's the parallel component of gravity here, which also points down the ramp, so it is also positive. And then minus the force of static friction. That points up the ramp, right, and it's mu sub s times the normal force. And I'm going to set that equal to 0. Since we're assuming everything's remaining at rest, the acceleration is equal to 0. Let's see. So next, let's look at our perpendicular equation. We have the normal force, which points out of the ramp. That's positive. And then we have the perpendicular component of gravity, which points into the ramp, so it's negative. Those are the only two forces on A that are perpendicular to the ramp. And I set them equal to 0. For mass B, I've got the sum of all y forces. That's going to be minus tension, right? Notice that, down is positive and tension points up, so it's negative. So there's the magnitude and direction for the tension, and then plus mbg. Gravity points down and down is positive, and that's also going to equal 0. Alright, so from this equation, I have that the normal force is equal to mag cosine 25. Well, let me back up for just a second. I want you to recognize that we've got three equations and three unknowns here. My unknowns are the tension force, the normal force, and mass B. So I'm going to circle all of my unknowns. Okay, so I have three unknowns. Two of them are repeated. Three equations, three unknowns. So when that's the case, you need to solve for a couple of your unknowns and substitute them. So here I solved for the normal force Alright, I'm going to use that. I'm going to plunk it right back up there. Next, I'm going to solve for the tension. I'm going to take this equation and solve for the tension. The tension is just equal to mBg. I'm going to take that solution and I'm going to plug it in right up here. Okay, so making those substitutions, I get mBg plus mag sine 25 minus mu sub s times mag cosine 25 is equal to 0. Alright, well, my only unknown is MB. So I have MB times 9.8 plus 49.7, and this works out to be 68.2. So MB works out to be 1.9 kilograms.